A local RAG demo is not useful if the index disappears every run. We'll use ChromaDB in Python to persist retrieval and debug what comes back. This is the workflow you'll know how to run when we're done, which persists your documents once, reloads the saved index, and inspects the answer with visible chunks. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Persistent local retrieval often breaks because people rebuild the index on every run. That kills iteration speed and makes debugging impossible when results drift. ChromaDB in Python is a small, local vector store that persists to disk so your embeddings and metadata survive process restarts. Success looks like a folder you can inspect, a collection you can reopen, and reproducible nearest neighbor answers you can audit. Intuitively, we want to put chunked text and fixed embeddings into a durable store, then ask the same question later and see which chunk answered it. Strengths are fast local development and repeatability. Weaknesses are that a local store is not a global service. So for big scale, you will swap to an ANN engine or hosted vector database. We will build a tiny example that writes 3 toy documents with reproducible 3-number embeddings, persists them, and then runs queries while showing which stored chunk matched. That makes the persistence problem obvious and fixable before you scale. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. To start, we need to open a persistent client that points at a disk path, so the index lives across runs. This snippet gives you a persistent client that points at a disk path, so the vector store survives process restarts. The import brings ChromaDB into scope. DB path names the directory on disk, and PersistentClient will create or reuse that folder right away, returning a client object you can reuse in later snippets. We call list collections, so you can see whether a previous run left collections behind. And the printed collections found tells you at a glance if you're starting fresh or extending an existing catalog. Now that we can open persistent storage, we need a deterministic way to add content so experiments are repeatable. This example seeds the persistent collection with deterministic toy docs and companion embeddings so results don't vary across runs. The records list pairs stable IDs with readable instructions, so the ingestion is transparent. The embed function encodes each string into a 3-number vector using character sums, space counts, and length. No external model, fully reproducible math. Client, get, or create collection uses the engineering guide's namespace if it already exists, avoiding duplicates. And collection.add persists IDs, documents, and embeddings together. The final print shows records after ingest at 3, confirming the index now holds those chunks. With data in place, the obvious next step is to query and inspect which chunk is considered closest to a question. This code asks the Chroma collection for neighbors using the same embedding logic so you can inspect which chunk ranks highest. The query string models a realistic operator intent, and embed query keeps encoding consistent with the stored vectors. Collection.query requests the 2 nearest neighbors and returns IDs, documents, and distances so you can inspect the raw payload. Because the result is columnar, result IDs 00 and result documents 00 give you the top hit, and distances quantify similarity. The prints reveal top ID and match distance, so you can confirm the guidance surfaced and how close the match is. Seeing a match is great, but we often want richer context or labels attached to IDs without recomputing embeddings. This snippet reopens the persistent client attaches topic labels to each ID, and inspects stored content without re-ingesting anything. ChromaDB, persistent client, points at the same DB path, proving a new process can resume from disk instantly. Get collection pulls engineering guides, so updates apply to the existing vectors instead of creating duplicates. The topics dict supplies human-friendly labels, and collection.update writes metadatas in place using only IDs and metadatas. Much faster than rebuilding embeddings. Peek then shows the first two records, giving you IDs and text previews to audit. And the print confirms the first chunk survived reload, and now carries a readable topic. Finally, we requery with metadata included, so the returned answer can be audited and routed. This example runs a fresh query through the enriched Chroma store to produce a minimal answer plus audit data. Collection.query requests 3 neighbors and includes metadatas, so topic tags travel with each hit. We min over the zipped IDs, documents, distances, and metadatas to pick the lowest distance candidate, returning both the chunk text and its topic. Best meta exposes the label we added earlier, and the assembled answer string stitches together topic, question, and retrieved content into one reproducible reply you can inspect or log. The print highlights final ID and answer length, so you know which chunk powered the response and how much text your pipeline would pass downstream. Applied to a real project, you would swap the toy embedder for a production encoder, keep the same persistence pattern, and use topics for routing or filtering before you call a language model. Recap: use a persistent ChromaDB client to stop rebuilding your index every run. You get a local folder you can inspect, reproducible nearest neighbor answers, and faster iteration during development. Reach for this pattern when you need quick, auditable retrieval in a local RAG prototype. One caveat: local persistence is excellent for development, but for very large datasets, you'll likely move to a scalable ANN or hosted vector service. Next step: scale the same approach by adding an ANN index or benchmarking latency and accuracy as your corpus grows to hundreds or thousands of chunks. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.